Okay, dear friends, hoping that you are all fine and you are charged up for your exam right now. And physics IGCSE 0625 or 0972 physics exam is coming soon on 9th of May. And I'm happy that you will be, and I'm expecting that you people are working hard to get the best grades. Here, I'm right now recording this electricity magnetism revision lesson. It will be 1 hour plus duration. All the key points I'm going to discuss with people. And I'm sure they will be helpful and handy for you people. And without any delay, let's start. So first of all, properties of a magnet. So if we talk about the magnetic materials, these are the materials which are attracted to magnets. Mainly the ferrous metal like iron and steel and their alloys. Cobalt, nickel, and certain alloys are also magnetic materials. So materials can all be magnetized to form a magnet. And keep in your mind, from 2023 onward, magnetization and demagnetization are not directly part of our syllabus. So we don't need to work on how to magnetize and how to demagnetize a magnetic material. Yes, electromagnets are there. So demagnetization and magnetization is not part of our syllabus. So magnetic materials are the materials which are attracted to the magnets. And examples iron and steel. Their properties we are going to discuss very soon. Then non-magnetic materials are materials which are not attracted by magnets and cannot be magnetized to form a magnet. And the examples are so many: wood, rubber, glass, etc., etc. They are all non-magnetic materials. Also remember, copper is a very good conductor of heat and electricity, but copper is also not a magnetic material. Very common, you can say, misconception. Now, this is also very important. Remember that like poles repel, and unlike poles or opposite poles, they do attract. And also remember one thing, that if you are going to check that either a material is a magnet or it is a magnetic material, when we are bringing a material close to a magnet and it is attracting. So it is a proof that the material is also a magnetic material. But if we reverse the direction of the magnetic material and bring it again close to the magnet and it is repelled by the magnet. So this is a confirmation that the material which is brought closer to the magnet is also a magnet. So remember, any material repelled by a magnet is the confirmation that that material is also a magnet. Okay, let's move forward. Induced magnetism. An unmagnetized material, magnetic material can be magnetized by bringing it close to or by touching a magnet. This is called induced magnetism. Now here you can see on one side there are steel paper clips and other side is iron nail. So they are brought closer. So you can see here that these paper clips, first clip is attracted to the magnet south pole. And see, this is south, north, then south, north, because unlike poles, they do attract. On the other side, iron, here is north, so south, north, south, and so on. Now, so they are all attracted. This way to magnetize is known as induced magnetism. Iron is an example of soft magnetic material. Now, classification between iron and steel. What does it mean? It means a material that loses its magnetism easily and unmagnetized easily. The induced magnetism in iron is temporary. Soft magnetic materials are used to make temporary magnets like the electromagnets and cores of different materials. Also, one thing more. If these iron nails are separated from the magnet and they are allowed to fall, they will fall apart. In other words, they will never be sticking together after separated from the magnet. The reason, they are quickly magnetized and they are also quickly demagnetized. So magnetism will be no more available with them when they are not attached to this magnet. On the other hand, now steel. We will read its definition, but steel, these paper clips, even removed, they are separated from the south pole of the magnet, but still some of them, or maybe all four, they will be sticking together. They will be attracted towards each other. The reason for that, steel is a hard magnetic material. It is not losing its magnetism quickly. So it means all the materials, bar magnets, which we are finding placed in our schools physics labs, they are made up of steel or any other hard magnetic material. So steel is an example of hard magnetic material, one that is harder to magnetize but also harder to unmagnetize. The induced magnetism is permanent. Hard magnetic materials used to make permanent magnets like a loudspeaker and so on and so on. Okay, dear friends, let's move to magnetic fields. Very common definition nowadays in exams is a region in space where magnet experiences a force, or even we can say where the North Pole experiences a force. So figure shows the magnetic field around the bar magnet. So this one is a bar magnet, like a chocolate bar. This is shaped like this. So it is the magnetic field pattern around the magnet. But here one thing very important. Remember, see, these lines of force are pointing from north towards south. They are pointing from north towards south. So I have not written a lot, just to the point, so that in 1 hour or so, I can go through quickly the all important points of this electricity and magnetism. So they are all pointing from north towards south. So if I'm told to draw here magnetic compass, so the magnetic compass will be pointing this way, and here also pointing in the same way. Here the magnetic force, the magnetic compass pointing this way. Here also it will be pointing outwards. So magnetic field lines come out from north and go into south. The places where the lines are closer together, field will be strong. And the region or places where the lines are further apart, field will be weaker. Okay. So next is now electromagnet. Is a temporary magnet produced by passing an electric current through a coil of wire wound on a soft iron core. And always remember that core material is always iron, soft iron, quickly magnetized, quickly demagnetized. The soft iron core is magnetized only when there is a current in the wire. And let me tell you, the current is DC, direct current, a current that keep on flowing in the same direction. And also remember, a cell or a battery, they are the sources of direct current. Okay. So, and also one more definition for this electromagnet, even we will be sometime calling it a solenoid, but electromagnet, its magnetism can be turned on and off many times a minute. You turn on the current, magnetism is also turned on. It becomes a magnet. You turn off the current, direct current, I mean, magnetism will be vanished. No more magnetism will be available. So the strength of an electromagnet can be increased by, this is a recall memory, many times in exams, increasing the current, because this magnetism is caused by current, increasing the number of turns in the coil. But let me add here something, but in the same space, so that concentration of the field is more. Move the poles together, and here they have moved the poles together already. The poles are moved closer together. Okay, dear friends, let's move forward. Now, electrostatics mean producing charges and their properties. Rubbing an object makes it charge because the friction causes the electrons to be transferred from one material to another. From one material to the other. So it means electrons are responsible for any material to be charged. So if flow of electron is there, so a body losing the electrons, it will become positively charged. And the body gaining the electrons, it will become negatively charged. So the material gaining electrons become negatively charged. It now has more electrons than protons. Similarly, material losing electrons becomes positively charged. It now has fewer electrons than proton. The number of electrons are less than protons. So don't be confused that protons are flowing. That's why an object is becoming positively charged. No, it is only the flow of electrons which makes one material positively charged and the other material negatively charged. And how? I told you already here. Electrical conductors are materials in which electrons can move freely from atom to atom. It is the definition in terms of electrons. So electric charge can flow easily. All metals and some forms of carbon are conductors. Electrical insulators are materials in which electrons are firmly held in their atoms. So they are not free to move and cannot move. So electric charge cannot flow. Most plastic are good insulators. Wood is an insulator, plastic is an insulator, rubber is insulator, and so on. Now, just like magnetic field, there will be also electric field. Electric field is a region in space where an electric charge experiences a force. Just like magnetic field is a region of space where the North Pole experiences a magnetic force. Here you can say where is an electric charge experiences an electric force even. The field can be represented by the lines of force in the direction that a positive charge would move if placed at that point in the field. At that point in the field. And here you can observe one thing very important, that from positive charge, lines are drawn outward, and from negative charge, lines are drawn inward. And same pattern here, that lines of force are moving from positive towards, are directed from positive towards negative. Lines of force are directed from positive towards negative. And sometime in exam, very commonly, you are told that this is a negatively charged particle. Draw the lines of force. 1, 2, 3, 4 lines you can draw like this. No need to draw this much. It is negatively charged, so arrowhead is needed, which will be pointing inward. Very common question. And if the lines are, if the lines we have to draw between two oppositely charged plates, so then they will be always flowing from positive, not flowing, pointing from positive towards negative. So like here you can see. And also one thing more very important. Let's go, this distance is 2 centimeters. This one is also 2 centimeters. If the separation between the lines of force is equal, it means field is uniform. It means electric field is uniform. So here electric field is uniform. That's electric current. Defined as the rate of flow of electric charge in a conductor. Electric charge is equal to electric current, is equal to electric charge over time. Current is denoted by I, charge is denoted by Q, small or capital, and time small t. So I is equal to Q over T. And by the way, the unit of current, I did not put here. So unit is ampere, denoted by capital letter A, and charge unit is coulomb. T over time unit is second, that is denoted by S. So we can say ampere is equal to coulomb per second. And also one thing more, sometimes we are given with number of charge carriers and the charge on one particle, like electron, and we are asked to calculate total charge. So remember, Q in that case, Q is equal to N times E. Q is equal to N times E. Q is total charge. N is number of charge carriers. What does it mean? It means how many number of electrons are there, how many number of protons are there, like this. And E is the charge on one electron or proton. I'm sure this is clear, but this is very important, this one equation. Okay, how to measure current? The size of electric current in a circuit is measured by ammeter. Basically, this is the ampere meter. So M meter, altogether ammeter, and it is always connected in series in the circuit. And what do we mean by series? It means there is only one path for the flow of current. There is only one path for the flow of current. Even you can see here, always we are giving the direction of current from positive terminal of the battery towards the negative terminal of the battery. So current is flowing from positive to negative. So this is the flow of current. Flow of current. Always. And in general, we call it conventional current. This is the symbol for ammeter. This is the symbol for lamp. And this is a battery. As I told you in the beginning, battery is a source of direct current. And if we are asked to draw or to show the direction of electrons, flow of electrons, flow of electrons will be opposite to the direction of current. It will be from negative towards the positive terminal of battery. So this is the flow of electrons. Flow of electrons. Okay, dear friends. Now voltage. It is the measure of amount of energy per unit charge. It is denoted by letter V. You will denote voltage by capital letter V. So mathematically we can say voltage is equal to work done per unit charge, or voltage is equal to energy transferred per unit charge. Both these equations are very important, and voltage is measured in a unit called volt, and that is also by denoted by capital letter V. So energy transferred per unit charge or work done per unit charge, because work done is equal to energy transferred. So both the ways it's okay. Work done per unit charge or energy transferred per unit charge is equal to voltage. Unit is volt, and then we are classifying it into two forms. One is electromotive force, other one is the potential difference. So electromotive force is the electrical work done by a source in moving a unit charge around a complete circuit. It is mostly coming in exam for 2 marks. After writing this definition, you can simply also write for the second mark that V is equal to work done per unit charge. So you can write this equation W over Q. So work done by a source means like battery, in moving a unit charge around a complete circuit. It is V is equal to W over Q for second mark, measured in volts, and volt will be denoted by capital letter V, just like the voltage is denoted by capital letter V. What about potential difference? That is also a type of voltage. Across a component, potential difference across a component is the work done by unit charge passing through the component. In other words, people used to call it electrical energy at work. It is measured in also volts. So work done by unit charge passing through a component or between 2 points in a circuit. That is potential difference, and better also to write in the end V is equal to W over Q. Very important. You must remember this definition. These are repeated definitions in exam. These are repeated definitions in exam. Then measuring potential difference or electromotive force. So we can measure the potential difference or electromotive force by using a voltmeter. And voltmeter is always connected in a circuit across the component. Here it is across the length. So potential difference across the length. Here it is measuring the EMF of the cell. So here it is measuring EMF and here it is measuring what? Potential difference. But in both the ways, voltmeter is always connected in parallel to the component or across the component. Anyway, you can write. And also one thing more, if you are making voltmeter like this, it will be considered wrong. If you are making ammeter like this in circuit, wrong. What to do? Make a circle like this and then write V. And also lamp symbol, very important circle. And this cross must be touching the surface or circumference and then make a, this is okay, this is okay. But if you are trying to make a lamp like this is wrong, not okay. This is also wrong. Okay, so I'm sure you are getting my point. Now, two types of current. Alternating current. A current that keep on reversing, changing direction with time is called alternating current. This one. So this is current time. So you can see it keep on reversing the direction. Here also, this is current and time. So it flows all in the same direction, all the time in the same direction. So a current that flows only in one direction all the time is called direct current. Okay, dear friends, let's move forward. Now resistance is the opposition of a conductor to the flow of electric current. And resistance is inversely proportional to current from Ohm's law. Ohm's law statement I did not write here, but remember that mathematically, if we write Ohm's law, the statement of Ohm's law, V is equal to IR. In other words, current flowing through a conductor is directly proportional to the EMF across the conductor. EMF provided by the source. Provided, okay, again I'm repeating, current flowing through a conductor is proportional to the EMF supplied by the power supply. Provided resistance of the circuit remains constant. To keep the resistance constant, it means temperature should be constant. Dimensions of the circuit components like wires must be constant. So, resistance is the opposition to the flow of current. If resistance is higher, current will be low. So I can manage it this way. Current is inversely proportional to resistance when the voltage is kept to what? Same. So if the resistance of the circuit will be more, for the same battery or voltage, current will be less. And we can find it, R is equal to V over I. And resistance is basically caused by collisions between the electrons and atoms. You can say electrons and ions. Anyway, you can say. So it is caused by collisions. But resistance is measured in ohm. So potential difference and current. So we can say ohm is equal to volt per ampere. Volt per ampere. Now some current voltage graphs. Very common. See, this is for a resistor, which is having constant resistance. Constant resistance. Here, this is for filament length. Initially, the resistance is constant. Up to here, graph is a straight line. But as the temperature of the filament lamp increases, resistance increases due to more collisions. As the electrons gain kinetic energy, so they move faster. So the probability of collisions also increases. So resistance increases, and as a result, current starts to decrease. So this is the IV graph for filament length. And here this is for a diode that let the current to flow only in one direction. So here you can see initially current is negligible, but then all of a sudden the value of current increases more quickly. And if you ask me, more correct way to draw it is like this. Initially, even voltage is increasing, but there is no current. And after a particular value of voltage, current exponentially increases, mean quick increase in the magnitude of current. So please remember these graphs, very important in exam. Paper 2 and paper 4, both. Now, resistance of a metal wire, in other words, the factors which are affecting the resistance of a metal wire. Again, resistance is caused by collisions between the electrons. And I have not drawn here for this Ohm's law. I can plot a graph here. Even the graph for Ohm's law, like current in amperes and voltage in volts. So graph will be a straight line. As long as Ohm's law is being obeyed, the graph will be a straight line. Okay, so like this constant value. And when the graph is a straight line, and it will be for mostly for metals, when the temperature is not very high. So we will call it ohmic. So now this graph is for ohmic conductor, mean a conductor which obeys Ohm's law. This one, these both graphs, they are for non-ohmic conductors because both these graphs are not obeying the Ohm's law. So non-ohmic conductors, their graph will not be a straight line. There will be no proportionality between current and voltage. So the resistance of a metal wire depends on length. The longer the wire, the greater the resistance. So we can say resistance is directly proportional to length. Similarly, cross-sectional area. So thicker the wire, the smaller the resistance. We can say resistance is inversely proportional to area of cross-section. Area is doubled, resistance is also doubled. Wrong. See, length is doubled, resistance is doubled. Length is made half, resistance of the wire will also be becoming half. Area is doubled, resistance will become half, inversely proportional. Area is made half, resistance is double. Also remember one thing very important, diameter. If the diameter is doubled, resistance will be decreased by 4 times. Why? Because area is pi r square. Diameter double mean area is increased by 4 times. And if the area is increased by 4 times, it means resistance will be decreased by 4 times. So remember, if the diameter is doubled, it means resistance will be decreased by 4 times. The reason behind that, again I'm saying, area of a wire, area of cross section, pi r square, diameter double mean radius is double, radius is increased. So it means as there is a square, so double the diameter, it means we are increasing the area by 4 times. So resistance will be decreased by 4 times. Remember, very important. And the last point, the material the wire is made from. Like metals, they have low resistance. Non-metals or insulators, they have higher resistance. Next is now electrical power. It is the rate at which electrical energy is transferred into an electrical circuit. Means speed of transferring energy, let me say in simple words. So we must know this equation, P is equal to IV for power, P is equal to I square R for power, and also P is equal to V square over R for power. You have to memorize these equations just like you are memorizing the mathematical formulas. Now, my dear, all these equations are to calculate power, electrical power, according to the given data. But there are some particular calculations with the help of it. Like this first equation is very commonly used to calculate current, which is power over voltage. Second one is very commonly used to calculate power dissipated, mean power which is wasted, which is spreading apart. Last one is used to find resistance by making, R is equal to V square over P. See, wherever I'm writing V, I'm using capital letter V. Also, this equation is used to compare the resistance. Okay, my dear friends. SI unit of power is what? As we know it already. Now, electrical energy calculations. Electrical energy is found by power times time. Why? No, from chapter 8. Power is equal to rate of transferring energy. If we are cross multiplying it and making energy as the subject of equation, so energy will be equal to power times time, or energy is equal to VI times T. So this is very commonly used in electrical circuits or electricity questions. VIT, WIT, VIT, just remember it WIT. V for voltage, I for current, and T for time. And mostly we are supposed to convert time from minutes or hours to seconds because unit is joules. System international unit is joules. So system international unit for time is seconds, not minutes, not hours. And another topic which was started from 2023, finding the cost of electrical energy. Always, first of all, we are supposed to calculate energy in kilowatt hour. This kilowatt hour is basically the commercial unit of energy. Let me write it here. Kilowatt hour is the commercial unit of energy. Even you can say electrical energy. Our electricity bills, we are saying how many units are consumed during the month. So 1 unit is basically kilowatt, 1 kilowatt hour. So energy in kilowatt hour, power must be in kilowatt, and time should be in hours. If power is in watts, so we will divide the power by 1000. See here, divide the power by 1000. Time in hours. How to find the cost of energy? Cost of electricity. Energy in kilowatt hour times the cost of 1 kilowatt hour. So important, remember it. Questions have started to come on this topic also. So very important thing, you have to convert the energy in kilowatt hour. And also don't be confused, only watt, kilowatt, megawatt. These are the units of power. But when it is kilowatt hour, time is involved. It is no more unit of power. It will be the unit of energy. Okay, dear friends, let's move forward. And first of all, we will be discussing some important circuit symbols. Symbol of a cell, positive, negative. Battery of cells. So many cells are connected. 2 are shown and rest, we don't know how many are there. So power supply, even you can say. DC power supply. Here 1, 2, and 3 cells are there. And if you ask me how much volts are there, 4.5 volts for if each cell is 1.5 volt. So here there are 4.5 volts. This is simple power supply, also known as power pack, also known as power source. Please remember all these things. This is for a AC power supply and alternating current power supply. If I'm writing here plus and minus, this will become DC power supply. Then now these symbols are very important and almost same with minor changes. Fixed resistor, variable resistor, same symbol but arrow. Heater, 1, 2, 3, 4 squares are there in between. Light dependent resistor, LDR, and thermistor. So these both are sensing resistors. Their resistances can be controlled by changing the light level in case of LDR And temperature, by changing the temperature, the resistance of thermistor can also be changed. Ammeter, we discussed already. Voltmeter, this is generator, which is a source of alternating current. Lamp switch, right now, this switch is open, which means the switch is off. But if it is like this, it means on, switch is on, or you will find in a question paper, close. Close means path is completed, no gap. Symbol of a transformer, magnetizing coil, relay switch, a motor, remember, like this is there. Fuse, then potential divider. The symbol has come already. Junction of conductors means three conductors are connected at this point. Earth or ground, diode, and if arrows are pointing outward, it is light emitting diode. Light emitting diode, shortcut we are using LED, and remember LED and LDR. These are two different things. They are not the same thing. You should be very good to draw and remember these symbols. Now, quickly, series circuit. Very important. Series circuit, in series circuit, there is just one path for the current to follow or for the current to flow. And that is here you can see only one path for the flow of current. And see, current entering is I, current leaving is I, current here is also I, current here is also I. Potential difference across R1 is V1, across R2 is V2, across R3 is V3. Okay, now some important points. The current at every point in series circuit is same, that is I, and I will add one thing, that for given resistances, if the resistances will be increased for the same battery, if the resistances in the circuit will be increased for the same battery, current will be decreased, but then it will be same. Magnitude will be decreased, but it will stay same through each component. Total resistance in series circuit is the sum of individual resistances R1 plus R2 plus R3. Then the potential difference across component series is equal to sum of potential differences across each component. So total potential difference or EMF of the supply is equal to V1 plus V2 plus V3. One thing more, very important, remember it. I am doing it here and considering it as 0.4. This is a tip for you people. I'm not going into a lot of detail. In series circuit or potential divider or potential divider. That is also a series circuit. Series circuit. Remember, V is directly proportional to R for same current. If in series circuit, a resistor is having greater magnitude, its share of potential difference from the battery sorry, will also be greater. Its share of potential difference from the battery will also be greater. So remember this point, very important. Another thing, another thing, in series circuit, if one of the component is disconnected, all other components are disconnected. The reason for that, because there is only one path for the flow of current. If that path is disconnected, so it means the path for all components is disconnected, which are in series. And remember this point, very important. V is directly proportional to R for current sake. It is will be workable in series circuit. Now, parallel circuit. In parallel circuit, There are alternative paths or branches of current. More than one path for the flow of current, it means it is a parallel circuit. Number, and you can see R1, R2, and you want to know how much is the potential difference across uh, R1, voltmeter is across R1. How much voltage across R2, voltage is across R2. You can even call it better. This is V1 and this is V2. Total current is I1. When it reaches it, in here, this is I1. Here also, this is I1, but it's split into I2 and I3. Let's suppose, if this I1 is 5 amperes, up to here 5 ampere, going out also 5 ampere. If R1 and R2 are equal resistances, then 2.5 ampere here, 2.5 ampere here, such that I1 is equal to I2 plus I3. 5 ampere is equal to 2.5 plus 2.5 ampere. Again 5 ampere. So current entering into a circuit is equal to the current, not circuit, current entering into a point is equal to the sum of the currents leaving from that point. If R1 was a smaller resistance, so current I2 will be greater. I2 will be what? Greater. Like maybe it is 4 ampere. Then definitely current I3 will be 1 ampere because total is 5. So 4 plus 1 equal to 5. Okay, dear friends. So when the components in parallel, the current from the source is greater than the current in each branch. I mean, you can see current from the source is 5 ampere and current in each branch is 2.5. So 2.5 is of course smaller than 5 ampere. That's what is the first point. Sum of the currents entering a junction is equal to sum of the currents leaving the junction. I told you already, entering the junction, I1. Leaving the junction, I2 and I3. So their sum will be equal to I2 plus I3. Point number two, potential difference across components in parallel is same. Across each component it is same. V1 equal to V2, that is equal to V3, let it be equal to V, which is the voltage of the EMF, or EMF of the supply, or sorry, voltage of the supply. What about the total resistance? Total resistance of two resistors is the sum of their reciprocals. Even I'm always telling the students, if you have to find total resistance for only two resistors in parallel, then simply multiply them in the numerator and add them in the denominator. This is for two resistors only. For two resistors in parallel. For more like 3, 4, 5, use one shortcut. For 3 or more resistors in parallel, you can simply write R total 1 over R1 plus 1 over R2 plus 1 over R3, so on, whole raised to the power -1. Do it like this instead of going with LCM and wasting your a lot of time. Okay. The combined resistance of components in parallel is less than the resistance of any one resistor. Even I will say even the least resistor. I can give you an example. Let me give you an example here. We are having R1 is 1 ohm. R2 is 5 ohms. So what will be the total? Only 2. So I'm using this formula. 5 times 1 over 5 plus 1. Answer will be even less than 1. Check. It is 5 over 6. And if I'm making 5 over 6, answer is 0.83. 0.8 ohm. So in parallel circuit, the total resistance is even less than the smallest in the combination. Like 1 ohm and 5 ohm. Smallest is 1 ohm. Total is even less than 1 ohm when these resistors are connected in parallel. Okay, dear friends. Then some sensing devices. Increase in resistance of a conductor. Consider a conductor with constant current flowing through it. The product of the resistance and the current gives the potential difference. V is equal to IR. This is Ohm's law. R is equal to V over I. So if the resistance of the conductor increases and the current remains constant, then potential difference across the conductor also increases. And this is for series circuit in general. As I told you even up there, that V is directly proportional to R for same current. And this point is repeated here. Now, sensory devices. Resistance of light dependent resistor falls with increasing light level. It can be connected in a circuit that require to respond changes in light level. And now I'm writing here. Let me write that resistance of LDR is inversely proportional to light level. Light level increases, resistance of LDR decreases, and vice versa. And its symbol, you should be very clear about its symbol. Sorry, not light emitted, light dependent resistance. Arrows will be pointing towards this. So this is the symbol of LDR, light dependent resistor. Then the resistance of thermistor decreases considerably with increasing temperature. With increasing temperature. So we can say also resistance of TH for thermistor is inversely proportional to temperature of thermistor. Temperature rises, resistance decreases. And the symbol, you must be very clear about the symbol like this. That is the symbol of thermistor. Then, my dear friends, next is relay. Switching circuits cannot power the appliances. They are switching on. For example, starting the motor of a washing machine when the water is at the correct temperature, a relay is switch turned on or off by an electromagnet, which is a temporary magnet. Now, this small current from the switching circuit switches the electromagnet, which attracts the switch, closing it, and the appliance is then turned on. How? See, only 5 volts. So when the switch is turned on, this electromagnet it is magnetized. So it will attract this relay switch. And see the AC main, high voltage will be turned on, and this device, which needs higher voltages, it will also be turned on indirectly. So we can say relay is an electromagnetic switch which is used to turn on high current circuit by using a low current circuit. So let me write the definition of relay. So So, relay is an electromagnetic switch used to turn on high current circuit by using low current circuit. Now, if you ask me, this one is a low current circuit, and this one is a high current circuit. High current circuit. So this is actually the scenario where this electromagnetic relay is used. And relay, it uses the magnetic effect of current. Relay uses the magnetic effect of current. We will study next fuse. Fuse is a safety equipment that uses the heating effect of current. In our syllabus, by the way, current has three major effects: magnetic effect, heating effect, chemical effect. Chemical effect is not part of our syllabus. So this relay is making use of the magnetic effect of current. Fuse, which will come later, that is making use of the heating effect of current. Now, light emitting diode. Light emitting diode will only light when forward biased, current in the direction of the arrow. Light LED must have a resistor in series with it to limit the current, as the diode have very low resistance in forward bias and can easily be damaged. They are useful as indicator lights. Before this LED, and we know the symbol for LED, you can say like this, light emitting diode. Here, I will just talk about a simple diode. Diode diode lets the current to flow in only one direction. In other words, it converts alternating current to direct current. How? Please see it here. This lamp will be on, and this diode is symbol of diode like this. So this diode is forward biased. So current greater than zero, resistance is negligible, and the lamp is on. Diode is forward biased. If I'm reversing either the diode or battery, it will be reverse biased and current will be no more flowing. Like if I'm taking it negative, positive, and diode is in the same place, in the same direction. Now again, there is a lamp here. No defect with the lamp, but it will be off now. Negative, positive. So now diode will be reverse biased. Current will be almost zero, resistance will be greater than zero, and lamp is off. Lamp is what? Lamp is off. Now, dear friends, next is the dangers of electricity. Like damaged insulation, there is insulation on the copper wire that is cut. So damaged insulation can lead to very high currents flowing in inappropriate places, like touching any human body, touching that place of the wire where the damaged insulation is there. This poses a danger of electric shock or fire. Cables that overheat owing to excessive current can lead to fire or damage the appliance or in the cable or insulation. Damp condition, wet conditions. Water is a conductor. Water lowers the resistance to earth. So damp conditions can lead to current shortening and can cause shocks. So that's why we are not recommended, we are not instructed to touch the electrical switches with the wet hands, or the switches when it is raining, and the switches which are in open outside, open area, and they are getting wet. So we are not supposed to touch them. So electrical devices for use in damp conditions must be designed to high standards of damp proving, especially connectors and switches. Overloading plugs, extension leads, or sockets which are long enough. If you have too many appliances plugged into one outlet, then the current will be too great. This can cause overheating, and also there is a chance of fire. Now, in the safety uses, fuses. Fuse is a piece of wire that melts and breaks when too much current is flowing through it. This switches off the circuit to protect against the shock, fire, or further damage. Fuses are placed in the live wire to safely switch off the device. Live wire, it is mentioned into the MCQs in the question in general, and also in series in the live wire. In series in the live wire, because in series, when the fuse will be off, it means current will be off throughout the circuit. And another important thing, fuse rating. This is the symbol of fuse, and this is the image of a fuse. What do we mean by fuse rating? Like this laptop, I'm just assuming this laptop uses 3 ampere current. So I'm told that I have options of 3 ampere fuse, 5 ampere fuse, 1 ampere fuse, and 7 ampere fuse. So which fuse rating will be suitable? Always remember, we are choosing the next higher value available. So here correct fuse for this purpose is this 5 ampere. You may be thinking 1 or 3. Due to heat, current can exceed even 3. So the correct fuse is always, you will see how much is the normal current for any electrical appliance when it is operating normally. So how much current is flowing through any electrical appliance when it is operating normally. So we are using the next higher value available. And again, remember, fuses are connected in the live wire in series, like a switch is connected. Switch is connected in live wire in series. Circuit breaker also is connected in live wire and also in series. Okay, now circuit breaker. Circuit breaker or switches contains electromagnets which, when the current is large enough, will separate contacts like we saw in the previous page or previous pages, will separate contacts and breaks the circuit. So currents will be stopped flowing, and a big damage or risk is saved. They operate quickly and can easily reset by pressing a button. And like this, you can find it, it is there in our homes. So right now this is off. If I will push this button up, press this button up, the circuit will be turned on again. Current in the circuit will be turned on. A circuit breaker is connected in live wire in series as switch and fuse. Now earthing. By mistake, appliances with metal cases have to be earthed using the earth wire. This is to protect against electric shock. For example, if the live wire became loose and touched the metal casing, the whole appliance would become live, carrying current. To prevent this happening, the earth wire is connected to the metal appliance and connected to the earth. So if the case became live, mean carrying current, a large current would pass through the live wire to the earth through the earth wire, the fuse will melt and will break the circuit, switching off the appliance. That is the same concept being used for these aeroplanes when they are being refueled. Even the oil tankers, there is also earth wire touching the ground alatul all the time because the body of the tanker it gets charged due to friction, so that all charge flows to the ground. Similarly, these aeroplanes are believed they are having conducting tires, so during the flight in air, their body is getting charged. If it is getting comprehensively charged, so as the wheels will be touching the ground, so all the charge will flow to the ground. So, like this earthing concept in action. Now, electromagnetic induction. When the magnetic field through a conductor changes and EMF is induced, this is called electromagnetic induction. So changing magnetic field through a conductor produces electricity. Shortcut. This change can be caused by a conductor moving through a magnetic field. Like in the diagram, you can check wire is being moved vertically, top to bottom or from bottom to top. So the field lines are being cut by this wire. In other words, magnetic field through this wire is changing and EMF is induced. And you can see it here on the meter. Electricity is there. Or magnetic field moving relative to a conductor. What does it mean? That this is the coil of wire connected to some galvanometer or ammeter, and a magnet is there. North and south, it is moved towards or away from this coil. So field is moving, magnet is moving, causing the electricity. Causing what? Causing the electricity. So there will be a relative motion basically. And what do we mean by relative motion? It means the distance between the coil and the magnet is continuously changing. As long as the distance will be changing, there will be a relative motion between the magnet and coil, and electricity will be generated. EMF will be induced. If both are at rest, like the magnet and coil, both are at rest, no relative motion, no magnetic field is changing, no electricity is generated. Both are moving in the same direction at the same speed, such that the distance between them is same. It means no relative motion. It means no electricity will be generated. Okay. Then here, this is the second example, as I told you. This is a coil and magnet is moved inward. So there is a relative motion. So electricity is being generated. Remember, an EMF is always induced when magnetic field through a conductor changes. If there is a complete circuit, current will also be induced. Factors affecting the size of an induced EMF. Very important. Recall memory, you can say it. Induced EMF increases with increase in speed of the relative motion of the magnet or coil. If you are moving this magnet towards and away, if you are moving the magnet towards and away very quickly, EMF induced will be higher. Number of turns of any coil. So increasing the number of turns, increasing the EMF induced. Strength of the magnet. If the magnet will be stronger, so the EMF induced, that will also be what? More, because more lines will be cut by the conductor. Because if the field is stronger, it means the lines are closer together. So more lines are being cut, more EMF is induced. Now finding the direction of induced EMF. Direction of induced EMF and induced current. We can find it by using the Fleming's right hand rule. Fleming's right hand rule. According to Fleming's right hand rule, if the first finger points in the direction of the magnetic field, F for finger and F for field, and the thumb, M, points in the direction of motion of the wire, then the second finger, C, points in the direction of the induced current, conventional current even, induced current, sorry, points in the direction of induced current. We can also see it this way. To remember it, we can use, first of all, right hand, not left hand, right hand. Thumb is perpendicular to the first finger. First finger is perpendicular to the second finger. I'm telling the students to remember it. Manchester United Football Club. Manchester United. Motion. M for Manchester United. M for motion. Football. F for football. F for field. Club. C for club. C for current. Induced current. So even you can remember it by Manchester United Football Club. Now remember, wherever we are dealing a case where electricity is generated, we will be applying Fleming's right hand rule. We will be applying Fleming's right hand rule. Okay, my dear friends. Next is then alternating current generator. Quickly we can discuss it. So when a coil of conducting wire, like this is the conducting wire, is rotating in a magnetic field by external energy source. Like I'm holding this wire from this handle and rotating it. Current is induced through the loop by the electromagnetic induction. Why? Because the distance between the coil and the magnet will be continuously changing, or the magnetic field lines are continuously being cut by this coil when this coil is rotating. So electricity is generated, EMF is induced by electromagnetic induction. In this way, mechanical energy is converted to electrical energy. This is the function of a generator, and this is a source of alternating current. Then, two things very quickly I would like to share. These are known as slip rings. What is the function of slip rings? The end carbon brushes, and these are carbon brushes. The AC generator has two slip rings. The function of slip rings is to rotate with the coil, and provide the alternate positive and negative induced current to the output carbon brushes. The carbon brushes are fixed with the body of the generator to maintain the contact with the rotating coil. So remember and memorize these definitions. Now here, this is just for your understanding point of view. See, when this coil is horizontal, current induced, voltage induced is maximum. Maximum lines are being cut by this coil. When this coil becomes vertical, lines are passing through the coil, not being cut, and check the voltage, it becomes zero. Again, after 180-degree cycle, half of the cycle, again the coil has become horizontal. See, again the voltage is maximum, but in opposite direction, negative. Again, when it becomes vertical, 0 volt. And then again, when it becomes horizontal, maximum voltage. So sometimes graph is given, so you should be very careful. So this is the graph of one complete cycle. Graph for one complete cycle of the coil. Okay. The next thing, which is very important, that is transformer. It is an electrical device that is used to increase or decrease the alternating EMF. It is used to increase or decrease the alternating EMF. It has three parts. Primary coil is one to which alternating EMF from AC main is applied either to step up or to step down. Mean whatever is our requirement. So AC mains, if we want to step up or want to step down, that will be connected to the primary coil of the transformer. Secondary coil is one which is connected to the external devices like TV, radio, doorbell accordingly. So secondary coil gives us the output voltage. Then iron core is one on which both primary and secondary coil are wound, and there is no electrical connection between primary and secondary coil, but they are magnetically linked with iron core. So no electrical connection between primary and secondary, but they are magnetically linked, and you can see it here. See, this is primary coil, this is secondary coil, then this is iron core. NP number of turns on primary, IP current in primary, VP voltage across primary. Similarly, VS voltage across secondary or voltage across the length. NS number of turns on secondary and IS is the current through the secondary. So this is the structure of transformer. How does a transformer work? This is coming in exam one way or the other way. So an alternating current applied to the primary produces an alternating magnetic field in it. Alternating magnetic field means changing magnetic field. Alternating magnetic field means changing magnetic field in it. So this magnetizes the iron core. This magnetizes the iron core. The iron core transfers this changing magnetic field to the secondary coil. How? Because secondary and primary coil both are connected on the iron core. So whatever the changes are taking place due to primary, same will be transferred quickly to the secondary. Secondary coil, being a conductor, cuts magnetic field lines and EMF is induced in the secondary coil. Please memorize it. Remember it as it is. It will be from 3 to 4 marks in exam. Now, what will happen if the direct current DC is applied to the primary coil? The magnetic field due to DC is static, not changing. If the magnetic field is not changing, so no EMF is induced in the secondary coil. Now, note that equation of transformer is Vp over Vs is equal to Np over Ns. Vp is what? Primary coil voltage. Secondary coil voltage is Vs. Np is the number of turns in the primary coil. Ns is the number of turns in the secondary coil. This is, it means the ratio of the voltage from primary to secondary equal to the ratio of the number of turns from primary to secondary. Here it is Vp over Vs is equal to Np over Ns. Even we can also write it Vs over Vp. If I'm flipping the voltage, I can also, then I will be also flipping the number of turns. Vs Ns in numerator, Vp Np in denominator. This one, this is a step down transformer. T for transformer. This is a step up transformer. Here, even we can observe number of turns are greater than number of turns on secondary. Number of turns on primary are greater than number of turns on secondary. Voltage on primary is greater than voltage across secondary. But current in primary will be less than current in secondary. Remember, I will prove it in front of you after a few moments. This is a step up transformer. Now here, my dear friends, number of turns on primary are less than the number of turns on secondary. So voltage on primary is less than voltage across, not on, it should be across, primary across secondary. And also current in primary will be greater than current in secondary. I will be proving it now, explaining it to you now. So you can observe this is secondary number of turns more, primary less, so voltage will be stepped down, but current will be stepped up at the same time. Power in a transformer. When you see a statement that for a transformer with 100% efficiency or a transformer with no energy losses, power in primary coil is equal to power in secondary coil. Power in primary coil is equal to power in secondary coil. So I will be explaining it to you here. Power. We know power is equal to voltage times current. That we studied in the start today. So power in primary, it means Vp times Ip. It should be equal to Vs times Is. Let's suppose 100 watt is the power in primary, then 100 watt will be the power in secondary. If the voltage is 100 volts, current will be only 1 ampere because 100 times 1 equal to 100. It must be equal to, if I'm making voltage only 2 volt, how much will be current? It will be 50 amperes. So you can check. That's what I was trying to tell you. Here voltage is high. So primary voltage is more. Primary current is low. When secondary voltage is low, current is what? High. So what can we say? See, in this case, this implies that Vp is greater than Vs, but Ip is less than Is. You can observe it here. And that's what I have written this point and this point. Numerically, we can prove. Now, this is very important. This rule is very important. So, even I can say in transformers, in 100% efficient transformers, current is inversely proportional to voltage and power is same. But this is only in case of transformers. This is only in case of transformers. Current is inversely proportional to voltage when power is same for a 100% efficient transformer or transformer with no energy losses. So this one is very important. How this is important? It is important in national grid system. Electricity is carried around the country by national grid system. So electricity is transmitted at very high voltage. Why? This is transmitted at very high voltage to reduce energy losses. To minimize the power loss in transmitting electricity, the current to be kept as low as possible. It means we can use a transformer, step-up transformer. This can only be this can only be achieved by increasing the voltage. The higher, if the reverse we are thinking, the higher the current, the more the transmission wires will be heated by current and more energy is wasted as heat. We don't want this. We want higher voltage of about 400,000 volts is achieved by using step-up transformers and transmitted through the national grid system. So when the voltage will be very high like this, current will be extremely low. So the heating effect of current will be very low. So very less electrical energy will be wasted as heat energy. Very less electrical energy will be wasted as heat energy. So that's the concept which is being used in this national grid system. And then this high voltage is reduced by some step down transformers to 230 volt before it is supplied to the homes. Then again it is stepped down to the required voltage. Okay, dear friends. Now, advantage of alternating current main supply. So this is used, why alternating current is used? To reduce the energy loss in transmission lines, because transformer does not work with direct current. It works only with alternating current. To decrease the cost of transmission cables, it requires thinner cables to transmit low ampere current. We have just discussed when the voltage becomes very high, current becomes very low. So if the current is low, we don't need to use thick wires. We can use very thin wires even. That will be workable. magnetic effects of electric current. Now, this is very important. A current carrying, a conductor carrying current produces a magnetic field around it. So, whenever current passes through a wire or a conductor, there is a magnetic field around it. If the strength of the magnetic field you want to increase the current flowing through that wire or coil. These points very important, please remember them. The strength of the magnetic field can be increased by increasing the current and vice versa. Mean if you will decrease the current, strength of the magnetic field will be less. If you will increase the current, strength of the magnetic field will be higher. Direction of magnetic field can be determined by using the right hand screw rule. According to this rule, if the right hand thumb, according to this rule, if the right hand thumb, like this is a wire and the current is upward, if the right hand thumb is held in a way that it is pointing toward the direction of conventional current, thumb is pointing in the direction of conventional current, then the curled fingers of the right hand, they give the direction of the magnetic field. So that's what here it is written. According to this rule, if the right hand thumb held in a way that it is pointing towards the direction of conventional current, then the direction of the rotation of the fingers give the direction of the magnetic field around the conductor. So if the direction of current is upward, see, lines are like this. So they are going anti-clockwise. And if the direction of current is reversed, thumb will be pointing in the downward direction. Before, magnetic field lines were anti-clockwise. Now they will be clockwise. So it means the direction of the magnetic field, caused by current, dependent on the direction of current. If the direction of the current is reversed, the direction of the magnetic field caused by current is also reversed. Now, my dear friends, as long as the current is flowing through the conductor, the magnetic field is present around it. When the current is stopped to flow, the magnetic field around the conductor is also vanished. Magnetic field is stronger, closer to the current carrying conductor, and is getting weaker as we move away from it. If you just give me a moment, see, let's suppose this is the wire which is carrying current outward, out of the page. So magnetic field lines around it will be the concentric circles. Roughly I'm making. So this is a wire. This is a wire with current out of the page. Out of the page. So it means like this. So thumb in the direction of current and the fingers will give the direction of magnetic field. So like this, 12, 11, 10, 9, 8, 7. So it means the direction of the magnetic field will be anti-clockwise. And this diagram is very commonly in paper 4. For 3 marks, they are saying draw the lines of magnetic field around a current carrying wire, and also current carrying wire, and also draw the direction of the magnetic field lines and how their strength is varying. That is also needed. How is varying? That is also needed, my dear friends. Okay, I'm sure you are with me. So, in this way, this magnetic effect of current we can discuss. Next, my dear friends, after this, let's continue to the magnetic field due to a solenoid. Right hand tool right now. Due to a solenoid. due to a solenoid. Now, a solenoid is a long cylindrical coil with a number of turns. It produces a magnetic field similar to that of a bar magnet when the electric current is passed through it. Inside the solenoid, the magnetic field is strongest and is uniform, while outside the solenoid, magnetic field gets weaker and non-uniform. Gets weaker and non-uniform. According to this rule, if the fingers of the right hand grip the solenoid in the direction of flow of conventional current, the thumb points towards the North Pole. Thumb points towards the North Pole. So you can see here now in this case, fingers are in the direction of current and thumb is pointing towards what? Towards the North Pole. Other side is of course what? That's the South Pole. Then relays and electric bells are good examples of use of magnetic field due to current carrying conductor. Now, how to increase, again recall memory, very important, how to increase the strength of magnetic field produced by a solenoid. Increase the number of turns of the coil, but in the same space, because this is a type of electromagnet already we discussed. Increase the current in the solenoid and also add soft iron core because it is quickly magnetized and also demagnetized on stopping the current. Now, electromagnetic effects. When a current carrying conductor is placed between magnetic poles, the conductor experiences motion due to a motor force. This is the concept of motor. So this force, this motor force, is a result of interaction of the following two magnetic fields. Which two magnetic fields? One is the magnetic field due to a magnet. One is the magnetic field due to a magnet. And the magnetic field, another magnetic field is the magnetic field around a current carrying conductor. So both these magnetic fields interact with each other to give rise to a force known as motor force, mechanical force, like this we can call motor force or mechanical force. Now, Fleming's left hand rule. According to this rule, extend the thumb, forefinger, and middle finger of the left hand in such a way that all three are mutually perpendicular to each other. So if the forefinger points in the direction of magnetic field, forefinger, first finger points in the direction of magnetic field from north to south pole, middle finger points in the direction of conventional current from positive to negative. Then thumb points in the direction of motor force. Thumb points in the direction of what? Thumb points in the direction of motor force. Then, my dear friends, DC electric motor. An electric motor converts electrical energy to mechanical energy or kinetic energy. An electric motor converts electrical energy to mechanical energy or kinetic energy. So when the current is switched on in the coil, it exists in opposite directions along the two sides of the coil. See, this way current is going in and here current is coming out. It generates equal but opposite motor force. That means couple, and it is rotating the coil. It is what? It is rotating the coil. So in this way, this motor is working, mean due to current, to different directions as we discussed in the beginning. If the direction of the current is reversed, the direction of the force is reversed. And this motor, it rotates. That is the function. But it either rotates clockwise or it rotates what? Anti-clockwise. Either it rotates clockwise or it rotates what? Anti-clockwise. So how to know? I have developed a very simple method, even without using Fleming's left-hand rule. See, the negative terminal of the battery is on the side of north. So N for negative, N for north. If they are on the same side, coil will rotate clockwise. So it means right turn. So left-hand side force will be up and right-hand side force will be what? It will be down. Then, in the end, commutator acts as a current reversing switch after every half cycle of revolution, such that motor continues to move in the same direction. Carbon brushes serve to make contacts between the battery and rotating commutators and keep them in place. Then the last point, factors to make the motor more powerful, increasing the number of turns, using the stronger magnet, and increasing the current. I'm sure this was a quick explanation. It will be helpful for you for your exams. Stay blessed. And if this video helps you to do share, like, and follow my channel and subscribe it if you have not subscribed it yet. And share it with your friends also who are especially taking the external exams of IGCSE this year. Thank you. Stay blessed. Take care. Bye.